Yes, so I think that we can start. So today we actually have the honor here to welcome Alexandru Iosuf from Freie University, where he's a full professor, tenured professor, and a group lead of the Massivizer Computer Systems Group. He actually he finished his PhD at Delft University, where he was associate professor. And during this time, actually, he also got, as I remember, awards for best researcher in Netherlands, 2016, yeah, and 2015 for best teacher in the whole Netherlands, which is quite a large achievement. Now, as I said, he leads the group in massivizing computer system, and his main research is basically focused in the area of ecosystems and how to improve the sustainability of systems, especially now in the computing continuum. And of course, as part of these activities, he is also the leader of the SPEC Cloud Group, where actually all these standards for cloud computing and these big ecosystems are decided. So now I have the pleasure or actually all of us have the pleasure today to see his presentation on the topic of massivizing computing systems. Alexandru, thank you. You can start.
Thanks, Draghi. Thanks very much. I guess the presentation is done. We can all go home now with all this. Yeah, so I'm indeed Alexandru Iosuf. I'd like to give you a view on operational data analytics, and if there's one thing this works. If there's one thing I'd hope you go home with is that it's a new name for, if you want, a new bottle for old wine. It's the idea that if we have the right processes, we can collect the right information about how our very large ICT infrastructure, very useful for the society in particular, how it works, and gain introspective powers and also therefore gain new abilities to optimize. That's it. Operational data analytics lets us understand more why systems work or do not work and what to do about improving them when we put them to good use. Yeah, so that's it. Yeah, I'd like to thank many people who are partially mentioned here. So, okay, you'll see a number of things. Let me start introducing who are the people. So I struggled with myself how many minutes to give for an introduction for our team. I started with 1 minute and I said 2, then 3, and now you see I cut it and it's now 5 minutes. So we're a large research team located at Freie Universiteit in Amsterdam. Amsterdam, you may know it, it's the city next to Schiphol. And in it, there are a couple of universities, and one of them I think is really nice. So we have about 25,000 students and about 5,000 staff members. Our team really works as a big science team. So we really work across all the aspects of the problems that we associate with large-scale infrastructure, whatever kinds of problems they may be. Types of hardware that are emerging, how to measure performance, how to improve different things. Are there ways of considering together all the different components, what applications exist and how to work them better into the society needs, etc. All of these things are things that we do here. You see some of the faces in the team. Here are some more of the faces of the team. So if there's one pattern that emerges every time in computer systems teams is that we are many. Yeah? You cannot do research in this field without actually having a lot of people. Has many advantages. We actually like to work with many people. Has a lot of disadvantages. We're expensive. I'll skip the introduction. I have the dubious pleasure of having a rather unique name. If you type it in Google, then it will be either me or the International Organization for Stand-Up Paddling. Apparently, we share the first position, and then from time to time, we do something with it. I've had the pleasure in the last 3 to 5 years of working with and putting together the local, so national community in computer systems. We each had our own views when we started, and when we finished this process, we actually can work together. We discovered that we're really powerful doing this. Feel free to read our manifesto, either scanning this or going to this address. There we indicate what we think would be the important topics for research in computer systems and networking in the Netherlands for the next 15 years. So if you want to go to the Netherlands for an internship, for a visit, for a collaboration, for a longer period of time, this is what we're doing and this is who we are. There's a who's who as well, so who's represented there. Long story short, one of the things that emerged from this is that, and these are these pillars here, is that we actually are quite useful for the Dutch society. Who would have guessed that, you know, scientists in their ivory towers actually have links with the society? Well, we're doing computer systems, they actually work, and society needs this kind of stuff. It needs this kind of stuff so much that the Dutch government has decided as one of the national strategic instruments of funding to fund us with 315 million over the next 7 years. And here the 75 plus partners represent, well, all the universities in the Netherlands plus about 60 companies. So I think it's a pretty nice consortium. What we want to do is to put together the national capabilities in advanced networking. 6G is around the corner. There are lots of capabilities there, from printing hardware to making it run well. And all the capabilities we have on the computing side, so cloud, edge, and endpoint devices. Together we call this the digital continuum. It's simply a lot of technology that we have tried for decades to put together, and now we think we have a chance to do so. If we are, then the expectation for all these grants is that for each euro they invest, they get about 10 back. So that would be the main criterion of measurement for the Dutch government. Okay, we'll see if this works. Something else that we do, we really like more researchy projects. So our science is around building computer systems that do interesting things. One of the more challenging things to do today is to work with a class of data that is, in a sense, the most irregular, the hardest, the most challenging to imagine, and that's big graphs. Graphs are a natural class of data that works across any kind of problem, so you can encode anything with graphs. Turns out, so mathematicians like this very much, the generality. A thing that they do not like very much, but we computer systems and networking people like very much, is that when you try to run even the simplest algorithm on even the smallest graph data set, you bump into how irregularly the algorithm accesses data and how much the resources that you're putting at the disposal of running this application, how much they're underutilized. That's a fantastic problem for a computer systems or networking person, because that's our bread and butter. That's what we do. We take these systems and we make them run really well and really efficiently. Yeah? And without us, you would basically be wasting more than 90% of all the infrastructure, which is way too expensive. Something else that we do, well, we try to help the community, so we organize some of the larger conferences around the world. CityGrid is around the corner, not only around the world, so I guess in 2 weeks we'll see some of us each other again. One of the things that I'm very proud of introducing in this overall conference is this point 8. Education in this field is really important. Computer systems and networks are difficult to teach to younger students in particular. They're very complex. They require many different components or knowledge items to be put together. So they're both broad and deep. That's really hard, and many students really struggle with this. We need new approaches to actually teach them. What do we do about it? So I'm very happy that this is starting to get international attention. Okay, I'm gonna check my timer. I'm already late, so we'll see what happens. My goal is, by the way, not to traverse every slide, and feel free to interrupt at any moment. I just speak fast, but that's a different question. So one of the things that I hope to convince you is that, me and my team were working on really important problems. To this end, I just want to tell you that, in my view, we live in a golden age of really large IT infrastructure. We call these computer ecosystems because they have these IT infrastructure have specific properties. What do I mean by it? I mean that we are really building general infrastructure that the society really can use every day. So what kinds of applications exist that can leverage whatever the infrastructure is? I'll introduce it in a second. Well, if you imagine, I've mentioned education. During the pandemic, we definitely moved online. So much of what we did actually needed to leverage computer systems for video streaming, for grading, for processing all sorts of things. Big science, probably I don't need to introduce this to you, but if you want to do anything in terms of astrophysics, chemistry, biology, bioinformatics, etc., the actual science is now measured a bit less by knowledge units and a bit more by the terabytes that you can process with the computing power that enables you to do so. And I can go on and on. I've just taught a few lectures here, and they were about online gaming, so I don't have to mention this. But if you're taking the bus in Klagenfurt, then absolutely, this is the equivalent icon for the Netherlands. If you're doing this in Klagenfurt, then you may have noticed that when some component is down somewhere that you may not even have an intuition exists, then the bus does not allow you to actually check in. So you can PIN, you can pay to the driver, but at some point, if the IT infrastructure doesn't work, the bus doesn't work. So a lot of our real world life has actually been digitalized to the point at which it stops working if some part that you may not even know exists stops working. That's starting to really affect a lot of people. So what's the infrastructure that I've been talking about? Well, I've mentioned 6G technologies for Wi-Fi. There's a lot of networking technology. 6G is particularly important because drawing wires requires really digging, and digging requires a lot of permitting that is very difficult to get these days. So we can't actually put more wires. It's extremely difficult. And instead of this, we're moving into the airspace where things are a bit more easily introduced, added, changed, etc. So that's a part that you see here. There are many other keywords there, terahertz, VLC, etc. I won't go into those, but there are many classes of networking technologies that will make the interconnectivity between whatever computer components we may imagine make it much better. And this is happening right now and definitely in the next decade. The other part, and this is where most of my work is, includes all sorts of large-scale infrastructure, starting with the largest, so supercomputers. Those are really very big data centers, very tightly interconnected. You may have, I don't know, tens of millions of cores in one machine. To clouds, those are more amenable, data centers, still very large, still 10 million cores or whatever, but spread a bit more and then with weaker capabilities, going through things like edge and smaller devices, IoT. So some of you in the room may actually be working with many of these things. Put together, they form this part, the computing continuum, together with this thing in the middle. That's the complete digital continuum. All right, so that's the playground. Now, one of the things that has happened in the last, I would say, 5 to 10 years, definitely in the last 5 years, has intensified, is that a lot of these applications which need to take important decisions, and we're doing so either with human beings in the lab that didn't scale, or with algorithmic approaches, all these have started to actually take decisions, perhaps better, perhaps weaker, I don't know, but take these decisions with artificial intelligence techniques. Two major classes that are dominant right now, machine learning, that's very much data-driven, and reinforcement learning, that's more algorithmically driven. Both of these classes of techniques are very compute-intensive, so every time we add a box somewhere here or there, it means that the infrastructure here needs to adjust. At this point, the adjustment is not only allowing things to run, but also making them run efficiently, because every box here means more equipment needs to be placed here, or the equipment that is here needs to be made more efficient. I'll mention the problem of efficiency a bit later when I say what's the scale of the problem. Now, once we tried to do this, we discovered, hey, we also have our own decisional problems in our own infrastructure, so we sprinkled our own infrastructure with AI capabilities, for better or worse, again. And we also discovered that many of these decision makers are made better when there's a lot of data around, especially machine learning techniques. Yeah? So everything in this universe in the last 5 to 10 years has been sprinkled with additional needs that we didn't know how to support a decade back. That's a very nice problem or challenge, right, for a computer scientist, and terrible for a society that depends on these things, because it means we're duct taping everything. All right, so that's my world. And what classes of things happen in this world? When one is that we actually need to run complex applications across these different devices. How do we do that? Well, we express them as workflows or data flows. And if you express anything that's complex into an even more complex language, one of the things that you may notice is that whatever you wrote one day may not be rerunnable, reproducible the next day, or 5 years down the line when Maaike has left the company. Yeah, tough luck. Good luck, Maaike, nice job, but okay, we stopped being able to run this thing. All right, so it turns out that figuring out how to define and how to reproduce workflows is a really big problem. Another thing that we noticed was that if you look at the devices here, they're each placed on a background of a different color, and these different colors are not there just because I want to be fancy with colors, but rather, every time we create an application that works on the devices on any of these colors, we pretty much lock in the application part to that particular set of devices. That's really bad news. Every time we want to run something across all of these devices, which is pretty much the dream of computer systems since the 1940s on, Yeah? Every time we do this, we need to actually port our application to a different independent silo of software and hardware. That's really bad news. That's something that the society cannot afford to pay for, re-implement each application every time for each part. But the good news is that if you analyze these different components, what they do, what they are, what they do, what kind of capabilities they have, conceptually, this is what's represented in this part. Conceptually, they're actually one and the same set of features, separated even in the same architectural layers, which is a very powerful statement if it's true. And second, if we can leverage it, we could even automate completely that applications run across all this infrastructure without further change. That's a big deal. What else? Well, we know that in this world, the business means creators of different applications reaching their target audience, and these creators make all classes of digital services. There may be games, that's a Pokemon Go, there may be streaming, I don't know, Netflix, there may be storage of different files like Dropbox, many other classes of services. Each of these digital services actually works in the same way today. Horizontally, you see as an axis time. And on the vertical axis, you see the intensity of the workload, which is generated by users accessing these digital services. Higher is, a request for more computational resources and networking resources to be available. Lower means those resources are not needed. One of the things to notice is this message over here, which says that every time someone clicks on a smartphone or issues in whatever form a request, that request is no longer satisfied by a monolithic application that just runs and returns the result. That's really old-fashioned. What happens now is that hundreds of different running services need to be orchestrated and together return a response. Yeah? That means those hundreds can be managed much more effectively if we're good at it, but also it indicates why I said a bit earlier the failure of even one service you don't know it even existed can actually crash the entire application. Yeah? Okay, now this workload requires, I said, computing resources and networks to actually run. Those computing resources are somewhere. Let's call them data centers of various scales. And a data center, a larger one, could even be, these machines stacked one on top of the other. On these machines, you get the different services. So something has to map that workload to the right machines at the right time and for the right duration. That something is a smart part of the system. It's called the resource manager and scheduler. And that's where we put a lot of effort to make this. You already know what the scheduler is. To be in this room at the right moment, you probably needed to leave another room at the right moment. Maybe with the right a bottle of water, you need to fill it up as well, right? All these are tasks to do with certain dependencies between them. And in our minds, we're pretty good at scheduling many things, including rather complex things. This stuff needs to schedule probably 1 billion times faster and more complex problems. That's what we're facing here. This is the resource manager and scheduler that exists inside one of these large installations. There are many of these, and they also need to work together. And also in between them, there are networks, and they also need to be properly managed and scheduled. So there's an enormous problem of resource management and scheduling for which we have, at this moment, a real need, but very little understanding of how this would actually work across the entire continuum. So a really big challenge. Last, but perhaps not least, I want to point out that many users of this infrastructure want to treat it the same way we treat any other daily utility. I'm not asking the buses in front, how they're repaired or what's the size of the gauge of the wheel or, what's the maximal speed or whatever. So in the same way, we don't want to know about this infrastructure the same kind of information. We want this infrastructure to be as fully automated as possible and yet return to us the needed information, what gets used, how much of it, with what climate impact, for what particular cost. Turns out that serverless computing promises to do this as, in a sense, a natural evolution of previous computing paradigms that were trying to do the same, but with a granularity that we've never used before. So before we could do these kinds of things, these kinds of problems, full automation, etc., for relatively simple workloads with granularities of seconds to minutes, which is already pretty good. That's what the cloud does. But now we're moving with serverless computing to any class of applications, so much more complex, and the granularity should be in the range of milliseconds, so 2-3 orders of magnitude finer grained information. That is really tough. Yeah? In computer systems, we say every problem changes completely, so transmogrifies into a completely new problem at 1 order of magnitude. Here we have 2 to 3 orders of magnitude per dimension and multiple dimensions. It's a real leap. It's really difficult to do. All right, so this then brings me to the point that it's not all rosy. It's not, you know, we've got this infrastructure that already powers the society, there's a lot of it, and, you know, it works. Turns out we cannot take it for granted. So the golden age comes with both the idea of generality and, what I want to introduce now, the idea of responsibility. Yeah? Before, when I was building systems, maybe 15, 20 years in the lab, I was a student maybe, you know, in the lab, I didn't think, you know, if I build this thing, how important will it be for the society? The deployment was not wide enough and not important enough for me to really care that much. Now I do care because about 2/3 of our economy actually depend every day on this infrastructure. So if something really works badly, then a very large part of our livelihoods actually goes away. That's significant. The other thing that we should be very worried about, and in the Netherlands we are really very worried about, is that the impact of this technology being so successful is that a lot more people are trying to use it. That's called the Jevons effect, and combined, which again says that if you have a technology and you've invented good techniques to actually use this technology, to create it, to use it, to put it to practice way more effectively and cheaply, therefore thinking, okay, but then I fixed the problem that I had. Well, the Jevons paradox is that in fact society says, no, the problem is now much larger. So you haven't fixed anything. Yeah? And the example that I normally give in class is, you know, so this was invented in Victorian England for, you know, the period of extracting, carbon, right, charcoal, and with it powering things via, you know, steam power. And initially it was for factories and for, I don't know, military ships. And then others in the society said, wait, but I also can use this. Yeah, let's make locomotives that could, you know, use this kind of engine. Yeah, and at some point somebody said, well, but let's make a clock that is steam powered. Yeah, you can still see those clocks today from places. You go to England, you can see them as museum pieces. But now with the digital technology, we're actually saying the same. We fixed it, especially for high performance computing. Many things really work very well. And now we want to use this for everything. And, you know, I don't have a steam clock, but I have a smartwatch. In 100 years, somebody will look and say, why did you do this? Why did you need a smartwatch? Yeah? Well, in the same way in which right now we say, why did you need a steam-powered clock? Right? Who uses a steam-powered clock? Okay, but the situation is very serious. In the last 5 years, the electricity, both globally, but I know the data specifically for the Netherlands, in the Netherlands from a bit under 1% of the electricity envelope for the country, data centers alone, so not the entire continuum, not the laptops for it, not the smartphones, yeah, are already a bit over 3% in just 5 years. And the prediction is, with AI technology coming into play, requiring a lot more, you remember those sprinkle pieces, yeah? Requiring a lot more computation and networking capabilities, we will be running into the 20-25% by 2035. That's a lot, because we cannot produce a lot more electricity. Yeah? There's simply no technological way right now. And by the way, the Netherlands is not super sunny, so it cannot produce a lot of that green stuff anyway. So either we move the entire Netherlands into Sahara, or we need to actually cut some of the growth. We need to be way more efficient. Yeah? I'm not even mentioning the dreaded word, we need to reduce the consumption of electricity. Yeah? This is only about electricity. There are many other elements of climate impact that we're right now starting to learn. Yeah? If you build a very large infrastructure and it heats up, well, you need to cool it off, and then where does that heat go? Hint, it used to go into a very large lake, yeah, next to Amsterdam, but then fish started to get cooked, so right now it's not going over there. Then what? Yeah, a lot of real questions that are starting to get prominent. Okay, what else happens? Well, very pragmatic things. If you have a lot of people using the infrastructure a lot more than the infrastructure can tolerate, then the infrastructure first slows down, so performance drops, and second, it crashes. Yeah, and I tend to give examples from gaming, because if you go to companies like, banks, and you say, this, let me give you an example from ABN AMRO, they get very upset. But it's the same situation. You can name any big societal application, I'll show you data and results that indicate they've had exactly this situation. Something else, I've mentioned that, we have a very large and nice research grant, right, in Europe together with you and with Radu and with you. So one of the nice things that is happening is that as graphs become larger and the information in them richer, we can actually build increasingly more useful applications for our society. And I think one of the really useful applications, Anna is over there, one of the useful applications for our society is LinkedIn, which tries to match, the people who are looking for jobs or looking for a network opportunity. Let's develop a project together. Who is the person that would be best suited to help me develop the next generation of technology and put it in practice? Well, let's look in our network and find an answer to this. Yeah? Even the simplest step of visualizing the network, this was a project that in 2012 LinkedIn introduced. They tried to do this for every user to just map their network. Very nice, it looks like this. And then we tried it with a network a bit larger. And then it said, your network is so large, sorry, it's too large to be computed. We are working to increase the limit, stay tuned. Well, we stayed tuned until the feature was discontinued because they simply could not run this at societal scale. And that's LinkedIn, a really good company with a lot of good engineering. Some other interesting things that are happening, there are technological trends that tell us that many of the free buffet that we've had in the field for like 6 decades, that's kind of ending. Horizontal axis is time, and one of the things that you've definitely heard about is Moore's law slowing down. Turns out we heard about it around 2005-06. That's the moment when we understood, because of physical effects, Dennard's scaling issues there, we couldn't cram more transistors into the same chip, but we still wanted a lot of transistors for a lot of computation. So what we did is we crammed more chips per card. Yeah? So we made things that are pretty much highly parallel, and we also put a lot of chips in many different places, and that's called distribution. Well, the bad news is that we're starting to actually learn that if we do this, the cost of data movement is so high that we're now spending about 35 times more energy for each instruction that we could do with other technology. That's a lot of energy wasted. All right, what else is happening? It turns out once you go to parallel and distributed systems, which I love, that's what I do, right? What you get are systems that do not behave like the nicely working, let's say, laptops and smartphones in front of us. These, especially distributed systems, don't have many of the properties we expect. They're not synchronized, data is not consistent. If someone changes something there, it's not reflected there. All these things need to be built. Something else that is happening is that we used to measure things by response time, so how fast things go, things of this nature. Turns out, as this becomes proper daily utility, those metrics need to actually evolve into things that belong to utilities. Like, what's the risk that the population doesn't have access to water? The same thing happens, what's the risk that the population doesn't have access to ICT infrastructure or to the ICT infrastructure provided by our company? Yeah? So things get increasingly more interesting. The other thing is the community is responding. So there are lots of new techniques that are being developed nowadays, but they work in isolation. They've been studied in isolation, they've been developed in isolation. How would they work together? We don't know. Yeah? So a lot of stuff is in need of change. Then one of the interesting things is that we don't even know who will effect this change because we're lacking millions of experts, about 500,000 in Europe, about 50,000, 60,000 in the Netherlands alone, and about the same number in the US. So if all the universities work at the current pace, we are just increasing the deficit. Yeah? We're just running behind. We don't have the people to actually run this stuff. All right. So I've told you enough about what doesn't work. I'll try to spend 20 minutes on what works. So the short story is that I think one of the missing ingredients in this entire way of thinking about large-scale infrastructure is that we are not thinking enough about how much data could help us. And then the notion that we want to collect, filter, process further, and analyze data continuously, this is what we call operational data analytics. Yeah? And I think as an idea, it's as old as computing infrastructures. I've definitely seen the early seeds of this, well, maybe not in the 1940s, but in the 1960s IBM mainframes. But we've never done this at this scale, at this granularity, at this complexity, and the differences are staggering. You can't use what we know about this from before. All right. What we'd like is a holistic view of how these systems work, how the applications run on top of them, so that we can say, first, if something happens to any part of this infrastructure or to the applications, we need to be able to say, why did it happen? And the second thing that I'd like to be able to say is, what can we do about that thing? How to improve it, how to change it. Turns out we're not the only science that thought data could be useful, so let me throw my pet peeve. Astrophysics, there they want to understand all sorts of mysteries of the universe by basically mapping it. And they've basically split it into different parts, and for each part they've launched very ambitious and expensive programs to map exactly that part in the right radio wave or whatever other wavelength. And when they do this kind of stuff, then they get Nobel Prizes and, I don't know, financing of about $1 billion, $1.5 billion per instrument, so that's roughly their range. But we also want to study our world, and we can also split it across many different classes of observational wavelengths. So that's what we did in our team for the past, I don't know, 15, 16 years, and it's beyond our team. I think we should do this more. If we do this correctly, perhaps the main promise is, based on what we know so far about using operational data to improve systems and to take better decisions in them, I think we have a good chance that if we make this systematic collection, processing, analysis, then, you know, ultimately we could find and eradicate every performance problem we have. Yeah? It's a bit the same promise that healthcare is giving you, right? If we can monitor and observe, then ultimately with good smarts, we're going to figure out how to eradicate disease. Well, the same thing happens here. I think there are other things for which data could be useful, but I don't have time to go over them now. This is the point in the presentation when I can, well, draw a breath and pitch that if we agree on these high-level statements, then it's a very good moment to think, how can we discuss further, not in this presentation, right, because that has a fixed format and rather narrow timeline, but, you know, to collaborate and start thinking together, hopefully as a community, about what operational data analytics really means and how it could be, well, built, thought about, used in practice, etc. There are many questions that I have myself, but you may have your own. Okay, this pitch being done, then let me give you some typical results. So these are things we've already done. Time allowing, I'm going to show you also some things that are in the pipeline, and we'll see. If not, the presentation slides are there. Feel free to have a look at them. All right, some of the discoveries we've made. One of them is what I call a phenomenon. A phenomenon is something that happens at larger scale, really repeatably, but we have no current laws or other forms of theory that explains them. So they exist in practice, we just don't know what they are. Yeah? All right, so what we noticed, this is for a large class of infrastructure called grid computing. Those are pretty much commodity off-the-shelf clusters, pretty large, that normally ran lots of applications for science. And the initial understanding about them was that they will replace the big supercomputers having roughly the same computational power, so roughly they will run the same problems, the same big parallel jobs. Well, turns out that in fact the bags of tasks, where tasks were executions of a single part of an application on a single processor, nothing parallel about it, and those different tasks in the bag could be executed in any order, independently, without correlating their results. That basically was the dominant model of execution in the grid. First, you see here the percentage of jobs that were executed there, and across all these environments, bags of tasks, jobs, so tasks in those bags of task jobs represented well over 80% of the workload, so dominant. But it could also be in such systems that, you know, it's just many users just launching commands like list my directory or what date is today or whatever, so not the real jobs. So we also looked at the use or consumption of resources, percentage-wise, the same different environments, large-scale grids in many different countries, still had largely a dominant component of bags of tasks, but we also saw this, Grid 5000, a research infrastructure for researchers in France to try out grid computing workloads and techniques to work with them better. They were at only about 25–30% of the resources being used were for these kinds of workloads. So for people who were not in my course a bit earlier, why do you think that happened? What does it mean? They were not like these others, right? So why not? What does it mean?
Almost endless resources.
Well, but then still, from the resources that were used, only that many were for bags of tasks. So they ran other things. Yeah. Why? They made collectively a mistake. They didn't understand that the dominant job was bags of tasks, and in this environment, they wanted to run representative workloads and test their own discoveries, their own systems, their own resource managers and schedulers, except they tested mostly on the wrong jobs. They just had no clue when they started, for many years, that they were focusing on the wrong problem. So operational data analytics can really help a community avoid wasting years. Yeah? This is basically, this part, you can consider it like between 100 and 200 PhD students wasting their PhD. Yeah, does it make sense? Just running things that are completely irrelevant. All right. From a more pragmatic perspective, we looked at the largest provider, the supercomputer provider for science in the Netherlands is paid from public money, so we had access to their operational traces. And we looked at thousands of metrics, from which here I selected just a few. And what we show here is how these metrics indicate that the system is cool, not much used for that particular part. So here CPU load, this is the cool part, so CPUs are not used here much. Or the red part, this part is used a lot. So one of the simple observations you can make here by correlating different things is that in this system, a lot of machines have hot GPUs. A lot of these machines had both CPUs and GPUs, and out of the two, they would use just the GPU. Yeah? And the CPUs were cold. So the recommendation that you can get to improve systems immediately out of this data is simply just buy less expensive CPUs. They're just not used. Why do you buy the most expensive thing in money and electricity use when they are not used at all? Just don't buy them. Yeah? All right, there are many other implications. There are ambitious projects to even eliminate the CPU altogether from the computing pipeline. NVIDIA is working on something like this. We'll see what happens. Then in the interest of time, I'm going to give another kind of result. So one of the things that you can do is when you talk about analysis, you can of course use statistical analysis, some mathematical analysis, but one of the more powerful and robust instruments that we actually have in the community is to build simulators that can capture very complex situations, especially non-linear effects, and do rather complex types of analysis. So here is an example. Our OpenDC works, it's a simulator, it's a discrete event simulator, works with both short-term analysis and long-term analysis. This is long-term analysis, and you can see from the dates that the period under investigation greatly exceeds any arrival pattern that you expect in such a system. Jobs arrive every day or every hour or every second, and now we want to analyze things for over a year. Now, what we looked at in this example is at the top, in the top subplot, you see the real, okay, that's my mark that I should start stopping. Anyway, so we looked at the increase in costs for electricity. These are real, taken from the market. And we hit the moment when the prices were increasing, but just before a certain war erupted, and then prices really increased. Yeah? The other thing that we started to look at is the cost of emitting CO2. And it turns out in many countries in Europe, there are now directives that say if you have a company that pollutes, it should pay something that goes into a sort of public kit, and hopefully, it pays at least for the, the lives that were affected, etc. So we took these values and we injected them in our simulator, and in our simulator we can replay entire operations of real-world data centers, of real-world companies, and then we can assess certain things. And we can assess tens of different metrics. This is a selection of the metrics that we look at. And again, these are numbers that are long-term. Yeah? So they take a long-term operation. So customers are often rewarded if the data center cannot meet the demand after the customer has signed a contract with the operator, a service level agreement, then the operator has to pay back certain penalties, and especially if the machines are not available, then they have to pay a lot. And it turns out, prior to our investigation into electricity, this was considered the most important, the dominant cost, the dominant risk, therefore, in operating data centers in the Netherlands. And there were others. But one important thing appears here with the electricity demand. Turns out the same operation consuming the same amount of electricity went from paying almost nothing to, because of the increasing cost in electricity, to paying a lot. And that a lot became the dominant cost of operation of data centers in the Netherlands. Before we did this study, we went to many different organizations in the Netherlands, maybe not many, but sufficiently many. And they told us, we're not that interested in the electricity cost. It's not important for us. And we went with the study and we said, well, this is what's happening, and you can predict what is going to happen if this continues to increase. And then the door started to open. Let's discuss how to work around energy. Yeah? Before this, nobody cares, unless you're an idealist. Yeah, that's nice for us, but companies are not idealistic. They make money. So this is a strong argument for them to invest in this. The other observation is, with all due respect, the Dutch government is not giving the right penalties for emitting CO2. You can see that the cost is not dominant in any form or shape. So that's not enough to incentivize companies to look at carbon emissions, let alone other climate impact things. All right, one fun fact. If you want to run experiments and have a good confidence that that they return correct results, you can either use good simulators or you can run your experiments real world. So the cost of running in simulation for us was about 112 core hours, about 2.1 kilowatt hours. That's probably what a normal human house consumes, maybe one day, or you can go from Delft to Rotterdam by car. But if we were to actually run the same experiments real world, we would have consumed about 55 billion times more. Yeah? So to get a first order approximation, I strongly encourage you to look at simulators, even if they might be inaccurate left and right, but the cost on the environment is significant. All right, one or two more things and then I should wrap up. So if you have really good operational data that you collect at the right level and you analyze in the right way, then you can actually scale up your applications, and some of them are really very intricate and really very demanding. Nothing is more interesting or more demanding than online games in my mind right now. And we took one of the harshest games to scale, Minecraft. Minecraft is super hard, not only because there are many players, but because the worlds are modifiable, which means no pre-baked, no pre-computed parts survive for long. So we took this and we built all sorts of techniques using what we call serverless computing. So I've told you a lot of automation. We automatically get parts of the game migrated to the right part of the continuum and then computed there, and then the results return. And then there are also algorithms for combining results that executed remotely versus locally. I don't know, all sorts of things. But one of the important things is that our resource management techniques, they're guided dynamically by monitoring information from the system that is collected real world, real time, fine-grained. And if you do this, then our servo, so our approach to this, it runs a real unmodified Minecraft server and client. It is fully compatible. Can actually support way more players. And in fact, with other results, we can show that we get even better performance for each player. Yeah? So that's something that you can do with operational data analytics. I don't have time to traverse reproducibility effects, so I'm going to maybe spend a bit of time in just a few ideas. So what can you do with operational data analytics? I've just mentioned that we can improve at the level of an application driven by real-world resource management and scheduling. You can improve the operation there. Turns out, at all layers in our infrastructure, you could actually get significant improvements by leveraging operational data. It shouldn't be a surprise, but often when you want to introduce a technology, you're asked, okay, but what proof do you have that it could work? Well, we've done ample surveys to know that in each of these parts, there are ways to leverage operational data. If only it were there, there are ways to use to leverage this operational data to improve these systems. What other ideas could you have? Well, a question could be, where does that information, where does the data come from? And normally, when you think operational data, you think someone like Amazon or Google or the data center is going to give you their monitoring data. Now, that's nice, but we took the data that they really don't like to show, like here is how much we failed, how much our services are unavailable, etc., and actually compared that with self-reported data reported by users. And it turns out users report way more failures and problems, especially localized, than cloud operators. So if a failure is large enough and strong enough and deep enough that it reaches the news, then the cloud operator will report it. If not, no. Yeah? There are strong disincentives for them to report that data, so we probably need to co-opt users and other application level sensors or other such things to collect proper information about how these systems work. We didn't know about this. We thought idealistically, you know, the monitoring systems are in place. How difficult can it be to get this data? Very. What else? I'll skip the ontology part. There needs to be a way to put together the data. One of the interesting things that we're doing is that we're trying to figure out, for a lot of applications that are data rich, whether they actually use this data, how do they use it, is it proper usage, do they respect privacy protocols, do they do everything that they say they do, etc. This can only be solved right now with the notion of tracing live how these applications work. We call this live provenance, and there's a little caveat. So we've built technology, including this one is novel for graph processing. There isn't anything like it right now, but we've built technology for provenance since I think the 1970s or 80s. Here is the caveat. The caveat is that the extra data that we need to collect just to figure out what happened could be easily tens of times larger than the data that we put into the project as input to the regular application. That's really bad news. Already we are talking about data that cannot be moved because it's too large, and now we say, well, collect 35 times more. Yeah? There's a lot of room for improvement. So we're building now the very foundational building blocks like provenance at this scale and this granularity, but we cannot operate with this at this moment. So we need to do something else. My last idea, then I will wrap up. So I've mentioned the analysis based on simulation. We now have a fancy name for it. It's called the digital twin. So a digital twin is a combination between a good process that collects relevant information about a real life process and a good simulator that can ingest the data and first replay or show what's the current situation, but also run all sorts of what-if scenarios and analysis of, you know, what would happen if there's a disaster, can we absorb it, etc. Now, in this project, Graph-Massivizer, we're also building one of these components, a digital twin for operations that are really complex. And what can it do? Well, Footprinter is the sub-component of the digital twin that needs to integrate all sorts of information, so the workload information, for example, applications that are running, the resource information, what resources exist there, and, rather novel, information about the electricity that is ingested into this infrastructure. Where was it produced? How was it produced? What's the carbon footprint of producing that electricity? If the sky is like this, then you get a bit of electricity produced by probably wind, given the strength of the wind, and a bit by sun. If it's 2 or 3 days ago, then it was almost, rain and snow even. Then zero sun, not so much wind power, because probably you're scared that the windmills will break down or something. So then to produce the same electricity that you would need, you would probably burn coal, and coal is really polluting. So this exact same operation, optimized in exactly the same way, has completely different climate footprint depending on what are the conditions around. So that needs to be assessed. All right, so assuming we have the simulator with some nice logos on it, what can we do with it? Well, one thing is that we can validate it, that it actually produces the results that, that reality actually would produce as well. So apparently we're at about 3% error, depending on the different measures. One of the things is that we can actually show, and I'll just say the conclusion here, and the conclusion is derived from how closely these two subplots are to each other versus how the top plot is versus the second. The main conclusion is you really need to understand that carbon emissions are primarily influenced by the carbon intensity of producing the electricity. Yeah? So if you do not include this in simulations, the rest is not relevant in terms of what you're actually having as climate impact. You could say, I'm optimizing for energy, etc. But if you're running exactly the same code the wrong day, then you would be basically polluting 100 times more than if you run it in the right day. Yeah? All right, so that's one conclusion. The other is that the location of the data center is really important. Yeah? There will be many kinds of games. Here, for instance, in this plot, horizontal axis is time, vertical axis are the carbon emissions normalized, right? So higher is worse. And what you see here, France, so locating things in France would have a fantastic carbon emission. You already know why this is happening. There's a lot of nuclear power there. Yeah? But nuclear is not clean either. So looking only at carbon emissions is also narrow. There's much more that we need to do there. Yeah? But with tools such as this. All right. Then I'll just wrap up with the take-home message and take any kind of questions. So I hope it wasn't too fast, too much, too whatever. But the point is, I think we have a fantastic large-scale ICT infrastructure, so information communication technologies put together. We've really moved into the golden age of such infrastructure with a lot of it coming in many different forms. We call this the digital continuum. It's great. It's really adopted everywhere. There's no question about it. But now the responsibility question is something we need to answer yesterday, if possible. Yeah? Because we're really running out of electricity and we're really creating climate impact that we don't even know about. So I think we have a good chance of tackling this problem, definitely in the next 5 to 10 to 15 years, by learning more, by knowing more about these kinds of infrastructures, simply by adding operational data analytics at scale. Thanks. That's the message.